SwayamPrabha.
Welcome. So we are doing approximation algorithm design using linear programming rounding, and in the last class we have seen that the vertex cover linear program is half integral. Now using that we will design a two-factor approximation algorithm for vertex cover. Let's recall the linear program. Minimize summation w of v times x of v xv over all vertices v in v subject to each edge being covered. Means for each edge E equal to u comma v in E. The constraint is xu plus xv is greater than equal to 1, and for all vertex v xv is greater than equal to 0, and this every extreme point is half integral in particular. Now, typical algorithms for solving linear program, for finding the optimum solution for linear program, outputs an extreme point. So, in particular, we can compute an optimal extreme point in polynomial time. Let x star v be an optimal extreme point. What our algorithm does is simply picks all those vertices whose corresponding variable the value is either half or 1. So, algorithm let W equal to V in V such that X star V is 1 or X star V is half. Output W. Claim the above algorithm has an approximation ratio of 2, of at most 2. Proof. The value of the objective function at X star, let's call this X star, is a lower bound on opt. So, opt is greater than equal to summation WV X star V, V in V. On the other hand, alg is summation V in W weight in V, weight of V. Now, this can be written as, this is less than equal to, for every vertex V in W, the value of X star V is at most 1. This is WV times twice X star V. This is twice V in W, WV X star V. But the vertices who are not in W, their X star value is 0. So, this is twice summation V in V WV X star V. But this is at most opt. This is at most opt. This is twice times opt. So, we have alg by opt is less than equal to 2, which concludes the proof. This is a typical LP rounding, that you solve the LP, take the solution, find out interesting structure and see how you can exploit it to design an approximation algorithm. So, you have seen two algorithms for this kind. One is F-factor approximation algorithm for set covered and two-factor approximation algorithm for vertex covered. Next, we see another interesting technique which is called randomized rounding. So, for that, let us apply it on set covered. Weighted set covered. So, let us write the linear programming relaxation, minimize summation sum over sets in the collection cost of S times x of S subject to constraint is for all element E in the universe over all sets S script is such that E belongs to S, X is, this should be greater than equal to 1. And we have for all set S in script X is greater than equal to 0. Okay. So now what we do is that we solve it. So let x star x star s in script be an optimal solution. Next, the approach is treat these numbers like x's. These are positive numbers, and for optimal solution, x star is lies in between 0 and 1. So treat x star is like probabilities of picking S. So in particular, the algorithm is for all set S in script S. So construct a solution. So let W be the set cover that we are constructing. Initialize it to empty set, and for all S, with probability x star is execute W is W union S, means for all S put S in the set cover that we are constructing with probability x star is, and we will see that this step, this with this just running this step once, all elements are covered with constant probability. Now we have seen in randomized algorithms that to boost the success probability, we need to execute some steps, execute the algorithm many times. So that's the third step. Repeat step 2, say L times. Let the analysis dictate how we should pick L, what should be the value of L, so that all elements are covered with say constant probability, with say probability at least say 99%. Okay, so analysis. First is, what is the probability that an element is covered by executing step 2 once? So let, so here is the claim. In one run of step 2, every element, let E be any element, for in one run of step 2, the element E or let us call it X, because this will come in the analysis also. So, let us call this A. The element A is covered with probability at least 1 minus 1 by E. Proof. So, what is the probability that an element is covered? So, is X star is here. So, let E is present in K sets in S1 to Sk in the collection. So, E will be covered if any one of them is picked. So, the element, this is A, if any one of S1 to Sk is picked. So, probability that A is covered is 1 minus probability that A is not covered. This is 1 minus probability A is not covered. This will happen if and only if none of S1 to Sk are covered, are picked. This is probability that none of S1 to Sk is picked. Now, each S1 to Sk are picked independently of each other. So, this is product K, sorry, I equal to 1 to K probability that Si is not picked. One minus product I equal to 1 to K. Si is not picked, that happens with probability 1 minus x star s. Okay. Now this can be written as 1 minus product I equal to 1 to k e to the power minus x star s. Since 1 plus lambda is less than equal to e to the power lambda for all real number lambda. So we apply this on minus x star of s. This is equal to 1 minus e to the power minus I equal to 1 to k x, this is si, x star is I. But what is summation of x star si? That is at least 1, because x star is a solution to this LP and S1 to Sk are the sets where this element A belongs. So this is at least 1. So this is greater than equal to 1 minus e to the power minus 1, which is 1 minus 1 by e, which concludes the proof. Now each element is covered with this much probability. Now what is the probability that all elements is covered? So probability that A is not covered after repeating step 2 L times. So what is the probability that A is covered is at least 1 minus 1 by E. So the probability that element A is not covered in one run of the algorithm of one run of step 2 is at most 1 by E, and each run is independent. So this is element A is not covered, this is at most 1 by E times to the power L. It means 1 by E times 1 by E L times, every time it is not covered. Now we want to ensure that this probability is 1 over poly n, because now at the end we need to do a union bound over all elements. So choose L equal to, let me write this way, this is less than equal to say 1 by n square. This is for what? This is choose L equal to twice ln n. Okay. So for L equal to twice ln n, this is 1 by n square. Now the probability, now do a union bound, using union bound we obtain probability that every element is covered. Is covered by W after executing step 2 twice ln n times, this is 1 minus probability that there exists an element A in U such that A is not covered by W after executing step 2 twice ln n times, this is greater than equal to 1 minus, now there are n elements, so n times we are adding 1 over n square, this is 1 minus 1 by n. Okay, so with probability at least 1 minus 1 by n, our algorithm outputs a valid set covered. Okay. Now, what is the approximation ratio, approximation guarantee? So, again the value of the objective function at an optimal point, that is a lower bound on optimal. So, opt is greater than equal to summation S in script S cost of S times x star of S. Okay. But what is alg? Alg is the output of the algorithm, it is the cost of the set W, and it is a randomized algorithm. So, we should be talking about expected value of alg, that is summation S in script S Cs times probability that S belongs to W. S is picked by the algorithm, but this is summation in one iteration it is picked with probability x star S, and in the worst case in each iteration and we run it for L iterations, and in the worst case all the sets that we pick could be disjoint, and so this is L times at most this, because if we pick the same set in two repetitions or two run of step 2, then we just store one copy. This is L is twice ln n x star s. But this is at most opt. This is twice ln n times opt. So hence we have expected value of alg by opt is less than equal to twice ln n. So it's the approximation factor is at most twice ln n. Okay, so we'll stop here today.